Every single day, vast networks of pipelines are moving resources all around us, but we never see them. And hidden inside these steel tubes are forces of incredible power, forces that engineers have to constantly predict and control to keep us all safe.
And the stakes? Yeah, they couldn't be higher. This quote says it all. A failure isn't just a simple leak, it can be absolutely catastrophic. And what's wild is that some of the biggest dangers are completely invisible.
So let me ask you this. What do you think happens when you slam the brakes on a river of liquid that's roaring through a steel tube? Well, the result is one of the most powerful and dangerous phenomena in all of pipeline engineering.
All right, first up, let's look at exactly what this force is. And trust me, they call it a hammer for a very, very good reason. You're about to see just how destructive it can be.
Okay, so the technical name is hydraulic surge, but it has a much cooler name, water hammer. See, when you suddenly stop the flow, like by slamming a valve shut, all that moving energy has to go somewhere, right? It instantly converts into this massive pressure wave, a shock wave that smashes through the pipe with the force of a literal hammer.
And the power we're talking about here is just immense. I mean, we've all seen this on the news, even if we didn't know what was causing it. Manhole covers launching into the air, huge geysers of water shooting up from the street. That's often a water hammer event. This isn't some small issue. It's a fundamental, catastrophic risk for any pipeline system.
This chart shows you exactly what it looks like. Just follow that top line. That's the fluid speed. It's moving along, and then bam, it drops to zero almost instantly when the valve closes. Now look at that red line at the bottom. Whoa, that's the pressure surge, a violent, instantaneous spike that puts the entire system under incredible stress.
So how does this hammer actually move through the pipe? It's not like the whole system feels it at once. It's actually a wave, and it follows its own rules of physics. This pressure spike doesn't hit the entire pipeline at the same time. Now, it travels out from the source, from that valve that just closed, at the speed of sound. But not the speed of sound in air, the speed of sound in that fluid. For water, that's almost 1,500 meters per second. We're talking over 3,300 miles an hour. This isn't a slow build, it's a shockwave racing through the system.
So how do engineers even begin to predict this? Well, there's a thing called Joukowski's law. Now, don't worry, we're not going to do the math, but it boils down to three key ingredients: how dense the fluid is, the speed of sound in it, and, this is the big one, how fast you change the flow. Basically, the faster you stop, the bigger the hammer.
And this table? Wow. This really puts the sheer scale of these forces into perspective. A sudden stop in a water pipeline can add an extra 24 bar of pressure. That's over 340 psi, more than 10 times the pressure in your car's tires, just appearing out of nowhere. Even for crude oil, you get a massive 17-bar spike. These are the kinds of forces that literally rupture steel.
Okay, so stopping too fast is the problem. The solution seems pretty obvious, doesn't it? Just go slower. But here's the thing about pipeline physics. The intuitive answer isn't always the right one.
I mean, this is the question every engineer starts with. To reduce the force of the hammer, you just cushion the blow. Close the valve over a longer period. It makes perfect sense.
But here's the twist. It turns out that for the really long pipelines that crisscross countries, closing a valve more slowly can actually create a higher pressure spike. Yeah, I know. How is that even possible?
Well, it all comes down to echoes, or in physics terms, wave reflection. That pressure wave we talked about travels all the way down the pipe, hits the end, and then it bounces right back. And the timing of that returning wave is absolutely critical. Okay, this chart is just incredible. It shows you what happens with different closing times. The red and blue lines are pretty fast closures, but now look at the green line. That's a much slower 30-second closure, and its peak pressure is actually higher than the others. That's because the reflecting wave is coming back and adding to the pressure that's still being generated by the slow closure. It's completely counterintuitive, and it's the kind of problem engineers live for.
So if you can't always trust your gut feeling, how in the world do you manage these forces? Simple. You build a perfect copy of the pipeline inside a computer, and then you try to break it in 1,000 different ways.
And this is the modern solution. It's called a digital twin. Think of it as the ultimate simulator. It's a virtual model of every single inch of the real-world pipeline. Every pipe, every pump, every valve. It lets engineers run any what-if scenario they can dream up, all completely safely inside a computer.
And you might wonder just how accurate these things are. Well, take a look. The thick colored lines are what the simulation predicted.
The thin gray lines behind them, that's the actual data from the real world. Whether a pump is starting up or shutting down, the digital twin is nearly identical to reality. That's the kind of accuracy that lets engineers sleep at night.
But here's the real magic. They can automate this whole analysis. The simulator can run hundreds of different scenarios and then just generate a report like this one, automatically flagging anytime the pressure goes too high. It pinpoints the exact location, the exact time, and exactly how bad it was. This isn't just data, it's a roadmap for preventing accidents.
And here's how they use it to find solutions. That red line shows a dangerous pressure surge going way above the safety limit. Not good. So in the simulation, they add a pressure relief valve. And now, look at the green line. The exact same event happens, but the relief valve does its job perfectly, and the pressure stays in the safe zone. They can test and prove a fix before anyone ever touches the real pipeline.
These simulations don't just model day-to-day stuff, though. They have to be able to model the absolute worst-case scenarios, the kinds of events where the very laws of physics inside the pipe start to get weird.
And that brings us to a concept called choked flow. This is what happens during a major rupture. The fluid escaping the pipe accelerates until its velocity hits the local speed of sound, and at that point, it just can't go any faster, no matter what. The flow is literally choked. It's hit its ultimate speed limit.
So why does that matter? Because knowing that absolute speed limit is everything when you're managing an emergency. It helps you accurately predict how much fluid is escaping, how quickly you need to shut a section down, and how to best protect the public and the environment.
When you really think about it, what we've seen is this hidden world of immense forces and truly brilliant engineering. This silent battle of prediction and control is happening 24/7 in the infrastructure we all depend on. It makes you wonder, doesn't it? What other invisible systems are being tamed right now just to keep our world in motion?